In this chapter, we're going to cover the basics of hypothesis testing and go over kind of the general theoretical idea and some practical applications. So I don't think this is new to many of you, and we've kind of casually used these symbols before, but I just want to make sure that everyone is familiar with the symbols for greater than and less than and greater than or equal to. And we'll use these when we talk about hypotheses. So a hypothesis is a statement of prediction that is testable. And generally, hypotheses predict the effect of an independent variable, which is something that experimenters manipulate, on a dependent variable. We'll talk about several different kind of configurations of hypotheses depending on which hypothesis test we're doing. But a hypothesis test in general is a statistical method that uses sample data to evaluate a hypothesis about the population. So the goal is to say that we've made a change, or a change that we see in the dependent variable comes from the independent variable and not from chance. We're trying to rule out chance. In the simplest form, we're testing whether a sample mean represents a population mean, but it gets more complex later on. But typically, we're kind of using a sample mean to evaluate a hypothesis about an unknown population mean. And so these are kind of the general steps that we take. We kind of start out with this expectation or this hypothesis about the population, and we're expecting that our sample will look very similar to the population. So we expect that our sample will be about the same. So if we want to kind of hypothesize that the average American has gained 15 pounds in the past year and a half of COVID quarantine, if we expect people to gain 15 pounds during COVID, then we expect that our sample will have gained 15 pounds. It won't be perfect because of sampling error, but it should be approximately that. So what we're going to do is we're going to get a random sample that ideally represents the population. So maybe we get a random sample of 300 Americans and ask about their weight gain during COVID. And then we're going to look at the obtained sample and see how does it look based on our predictions. If it's close to our predictions, then we can conclude that our hypothesis is accurate. If our sample gained an average of 13 pounds and we expected the population to gain 15, we might say, yeah, it seems pretty accurate. But if there's a big discrepancy between the data and predictions, we might decide our hypothesis is wrong. Maybe our sample only gained 3 pounds on average. So we're going to state the hypothesis about the population, use the hypothesis to predict the characteristics that the sample should have, obtain a sample about the population, and compare the data to the hypothesis prediction. In the examples that we're going to use today, a lot of what we're using is we will assume that we have a known population. So this won't be the case for all of the tests we do, but for today. And so let's say we have a known population that had a mean of 80 before the treatment, and we know that their standard deviation was 20. And so in this instance, we're enacting some kind of treatment, and we want to know what happens after the treatment is administered. Does it work? And what would happen if you administered the treatment to everyone in the population? But of course, we can only do this to a sample. So assuming that the treatment had an effect, it should be adding a constant to each score, which would mean we'd expect changes in the mean after treatment, but not changes in the standard deviation and no changes in the shape of the distribution. But again, we can't administer the treatment to everyone in a population. So we do research with a sample and see what that sample mean looks like. If our individuals in the sample are noticeably different from the individuals in the original population, then we have evidence that the treatment did in fact have an effect. And we assume that any difference between our sample and our population is because of the treatment. But of course, we have to remember from last chapter that it could also be due to sampling error, right? By random chance, in the example we did in the last chapter, you could get a bag of M&Ms that's 90% orange. Likewise, by random chance, we could get people whose symptoms are much lower than the population, and it could have nothing to do with the treatment. It could just be the sample that we got. So this is kind of the idea that we have to keep in the back of our minds. So this is kind of another demonstration of that same experiment where we have a known population with a mean of 80. We can't treat them all. So we're going to take a sample of them and administer a treatment. And we hope that the mean of the treated sample can tell us information about the mean of the treated population. So basically, the purpose of hypothesis testing is to decide if any differences we see are due to sampling error or to the treatment. Okay, so is the difference between the sample and the population, or let me rephrase. So the purpose of the hypothesis test is to decide between two explanations. One is the difference between the sample and the population is explained by sampling error, which would mean there's no effective treatment. Or is the difference between the sample and the population too big to be explained away by sampling error, and we do believe that our treatment had an effect. So the examples that we're going to start with today are all a one sample experiment. And the criteria for these is that we know the population mean in a specific condition, and we have to make some kind of extrapolation about that population based on our sample. So maybe we know the average IQ score, and we want to know if we give a sample of people this magic pill, if the magic pill will increase IQ. Okay, so what we're going to get is two different hypotheses. Okay, the null hypothesis describes the population parameters that the sample data represent if the predicted relationship does not exist. So the null is nothing, there's no effect. So the null hypothesis will always be some variation of no effect. So in this case, maybe the null hypothesis is that the pills don't influence IQ. The data all comes from the same population. The alternative hypothesis is always the one that you're really interested in. So the alternative hypothesis describes the population parameters that the sample data represent if the predicted relationship exists. So the alternative hypothesis is really probably what you actually are interested in. If there's no effect, there's no purpose in doing the study, right? So we choose the alternative. The alternative hypothesis is generally that there is some effect. And again, exactly what this effect will look like depends on the type of experiment that you're doing. But the alternative is always there is some effect. So the alternative hypothesis might be that pills, these magic pills, do influence IQ in some way. Now, we always have to remember that we're not exactly sure what our distributions look like. With a one sample test, we know that the population without the pills looks roughly like this. It could be that these magic pills make no difference in IQ, in which case we'd expect to have just one curve that looks roughly like this. But it could be that people who take the pill are actually in a different population with a different distribution. So maybe taking one of these magic pills makes your IQ go much higher than people who don't take a pill, some amount higher. Okay, but it makes it bigger than the population average of 100. We don't know exactly what the pill is going to do, but we have to use the information we have to guess. So that's really what hypothesis testing is about. So we're going to go through a series of tests. And again, we're going to deal with a specific type of hypothesis test in this chapter, but the next few chapters are really going to be about different variations of hypothesis testing for different types of research questions and samples. So the first step is always to state the hypothesis about the unknown population. Remember, hypothesis testing is always about extrapolating to the hypothesis or to the population. So the null hypothesis is represented as H0. So 0, there's no effect. And so the null hypothesis means the effect is null, nothing happened. Basically, this is the treatment didn't work, there was no change, there were no differences between the groups. So the H stands for hypothesis, 0 indicates there was 0 effect. Okay, If we're in the context of an experiment, so if we're testing to see if an independent variable has an effect on the dependent variable, the null hypothesis would be something like the independent variable had no effect on the dependent variable. The alternative or alternate hypothesis is represented as H1. So again, the H stands for hypothesis. 1 is just the alternate. Occasionally you might have others, but we'll just deal with the null and the alternate. So the alternative hypothesis states that the treatment has some effect. There's a change in the general population following the intervention. The independent variable did something. The alternative hypothesis doesn't necessarily state what type of change there is, whether it gets bigger or smaller, but the alternative hypothesis is just there is a difference. So again, null hypothesis, there's no difference between groups. Alternative hypothesis or alternate hypothesis is there is a difference. Now, one of the key things with hypothesis testing is that we can never directly test the alternate hypothesis. So all of our tests are actually based on whether we retain the null hypothesis or whether we reject the null hypothesis. Okay, so this first step of hypothesis testing is to figure out what your null and alternative hypotheses are. The second step is to set the criteria for a decision. Okay, so we're going to use these criteria to evaluate the credibility of the null hypothesis. Do we believe the null hypothesis that there is no difference? Or do we say, no, we really think there actually is a difference? And the idea is that if there's a big discrepancy between the data and the null hypothesis, then we conclude the null hypothesis is wrong. So this is really where we come back to the sampling distribution of the mean. So remember that we have the population mean and we've selected a random sample from the population. And so our null hypothesis is that our sample came from the same population. Therefore, the sample mean should be similar to the population mean. And so what we're going to do here is use the sampling distribution of the mean to determine how likely it is that we would get our sample mean, or how likely it is that we would get a sample mean that's very close to versus very far from the population mean. Okay, so where this comes in terms of the criteria for the decision is the alpha level. So in order to figure out at what point we say, well, that sample mean is pretty close to the population mean, I think it came from the same sample, versus when do we say it's really unlikely that this population mean or that this sample came from the same population. We have to establish some kind of cutoff. So if we say it's really unlikely that this sample came from the same population, probably that sample mean is going to fall in the tails of the distribution that were of the population distribution. And so if we think that our sample came from the same population, that's consistent with our null hypothesis. If we think the sample came from a different population, that would be consistent with our alternate hypothesis. Okay, so we are going to select a specific value, which is called a level of significance or the alpha level. And this is the criterion or cutoff for making a decision about whether we accept the null hypothesis and say, yeah, it probably came from the same population, or if we reject it. We'll get to type 1 error in just a second, but the alpha level determines the risk of type 1 error. The most commonly used alpha level is 0.05. You can assume that unless it's otherwise stated. But what an alpha of 0.05 means is that we are separating the extreme 5% in the tails from the 95% in the body of the distribution, okay? If our sample mean lies beyond the 5% cutoff or the 0.05 cutoff, it's extremely unlikely that it comes from the same population. So the 0.05 cutoff is associated with a z-score of plus or minus 1.96. So that's kind of our cutoff for saying, yes, this z-score falls in the tails. It's extremely unlikely that we would get this z-score. If the sample came from the same population. So when we have a z-score of plus or minus 1.96, or kind of something falls in the critical region outside of beyond the 0.05 level, we reject the null hypothesis that they're from the same population because it's extremely unlikely. So the critical region is outcomes that are very unlikely to occur if the null hypothesis is true, if the treatment had no effect. So the critical region is defined by sample means that are almost impossible to obtain if the treatment has no effect. So values that are really different from the population fall in the critical region. And we can go back to the unit normal table when we have determined our alpha level or our cutoff criterion. We can use that unit normal table to determine which z-scores are associated with that critical value. So that's where that plus or minus 1.96 comes from. Okay, so once we set this critical value, and this is something that the researchers set at the beginning of the study, it's almost always 0.05, but again, there are occasionally exceptions. Then you move on to step 3, which is comparing the sample means or data to the null hypothesis. So you should have formulated your hypotheses before you start data collection, in theory. So once you've established your hypothesis and alpha level, then you collect data. But the heart of statistics is really about comparing your sample data to your expectations and your hypotheses. Again, for today, we're going to focus on the z-score as the test statistic, but later we'll talk about other test statistics as well. So in order to compare our sample means to the null hypothesis, we compute a test statistic. When we're dealing with z-scores, we are looking at kind of a ratio comparing the obtained difference between a sample mean and a hypothesized population mean compared to the amount of difference we'd expect without any treatment. So the z-score basically describes where your sample score is located relative to the hypothesized population mean in the sample distribution of the mean. So you calculate this specific test statistic. And then in step 4, you make a decision. So you're going to use, in this case, the z-score from step 3 to make a decision based on the criteria you established in step 2. Okay, so there are 2 possible decisions that you might make. So the first is if the test statistic results are in the critical region, most often beyond 0.05, we conclude that the difference is significant or that treatment has a significant effect. And in this case, we reject the null hypothesis that there is no effect. Essentially, what this means is that we conclude that our treatment had an effect and accept the null hypothesis. Sorry. We conclude that the treatment had an effect and accept the alternate hypothesis. All right, so if our test statistic falls in the critical region, we reject the null hypothesis. It's important to note that we can never prove the alternate hypothesis because we don't have the population data. The best we can do is conclude that it's extremely unlikely that the null hypothesis is true and say, well, we reject the null hypothesis. And essentially the next logical step is, so we guess the alternate hypothesis must be true. If the data, be it a z-score or whatever test statistic you're using, is not in the critical region, then what that means is your sample mean is relatively close to your population mean. And so essentially this means that we don't have strong enough evidence that the null is wrong. And so what we say is we fail to reject the null hypothesis. Sometimes you might also hear that we retain the null hypothesis. We don't have enough information to say that the null is not true, so I guess it must be true, is essentially the logic here. So if you have a significant, or sometimes it's called a statistically significant result, it's very unlikely, we determined that these results would be very unlikely to occur if the null hypothesis were actually true. So you need to report your test statistic. And so it would look something like this. Wearing a red shirt has a significant effect on the size of tips left by customers. We report our test statistic. The p-value is the alpha level. So if it's less than 0.05, what that is indicating is there's less than a 0.05 chance that you would get that z if the null hypothesis were true. So that the p-value of less than 0.05 is essentially saying that yes, it fell in the critical region. There's less than a 0.05 probability you'd get these results by chance. So P is the probability of obtaining the sample mean in the critical region. When you have significant results, this probability is extremely small, less than 0.05. When it's not significant, what you say is you fail to reject the null hypothesis. So there was no evidence that red shirt had an effect on the size of tips left by customer. We're reporting our test statistic, and the probability of that occurring is greater than 0.05. So remember, we can only reject the null hypothesis with extreme scores, and those extreme scores, to get those, have a very small p-value. I also want to note that this is the way your textbook tells you to do it in terms of just saying whether p is greater than or less than 0.05. When you run analyses in SPSS, which hopefully we'll get to in a little bit, it will give you a specific p-value. And the norm in academic publications has kind of shifted to where, in general, you're expected to report the specific p-value, not just say that it's bigger or less than 0.05. So you use that bigger or smaller than alpha level to determine if it's significant, but when you're reporting your results, you do report the specific value. Okay, so let's say we've just decided that it's extremely unlikely we'd get the mean we found just by chance if the null hypothesis were true. But we've still allowed that there could be a 5% chance that it actually is true. This is set by alpha. Because our hypothesis testing relies on sample data, and because sample data are not completely reliable, there is always the risk that misleading data will cause the hypothesis test to reach a wrong conclusion. And so there are two types of errors that are possible. Okay, so this is a way to kind of set it up, the possible outcomes of a statistical decision. And remember, we're making a decision, but we don't know 100% what's true. We are taking our best guess based on the data. And so this gives us 4 types of possible outcomes for a statistical decision. My graduate stats professor always used to say, well, let's think about if there were a recording angel that somehow knows what's true. We don't know what's true. We're making our best guess. But maybe if there's a recording angel out there that actually knows the true values for the population, they would be able to identify whether, in fact, the null hypothesis is true and you have no effect, or whether there actually is an effect, and in reality, is the null hypothesis false? But of course, we don't know all the information, so we're stuck making our best guesses, essentially. And we decide, do we reject the null hypothesis and say, yeah, there is an effect, or do we retain the null hypothesis and say, there is no effect? Okay, so 4 possible outcomes. One is that we retain the null hypothesis and the null hypothesis is in fact true. There's no real effect here. So we made the right choice, yay. The second possible correct choice is that we decide this mean falls way in the critical region. There's no way that this can possibly be true if the null hypothesis were true, so we reject the null hypothesis. And if the reality is that, in fact, the null hypothesis is not true, there is a difference. Okay, so 2 possible correct decisions, but there's also 2 possible incorrect decisions. So we call these type 1 and type 2 error. Type 1 error is that we reject the null hypothesis, but the null hypothesis is actually true. So we say, there's no way that this mean comes from the same population, but actually it does. Or type 2 error is that we retain the null hypothesis, But in fact, the null hypothesis isn't true. So we've said, yeah, we don't have enough evidence to conclude that there's an effect, but actually there was an effect that we missed. Okay, so type 1 error again is when you reject the null hypothesis, but in fact there actually isn't a difference. So maybe you selected an unusual sample that scored really high or really low. So this is essentially a false positive. So this is the doctor checking out this guy saying you're pregnant, right? Obviously wrong. You've set up a hypothesis test so that this is very unlikely. And the likelihood of this happening is your alpha level. So you get to determine how much risk you're willing to accept, how willing you are to allow for this possibility of a false positive. And there can be some pretty serious consequences for this because the researcher concludes, so publishes and makes recommendations that there's an effect when actually there is an effect. Okay, so this becomes essentially an unintentional false report. But again, we set the likelihood for this, and this is alpha. And generally we say, okay, we're willing to allow for a very small 5% chance that maybe we accidentally say there's an effect when there's not really an effect. Type 2 errors are essentially a false negative. So here we've got a doctor checking out this obviously pregnant woman and saying, oh, you're not pregnant, right? False negative. So this is when you conclude that there was no effect, but in fact, there really was an effect. So you fail to reject the null hypothesis, but the treatment actually had an effect. Maybe it was a small effect, but if you'd been able to test the full population, it would actually be there. And type 2 errors most commonly result from very small treatment effect. So although the treatment does have an effect, it's not large enough to show up in a research study. So this is kind of like a bummer, right? There was a difference that you were looking for, but it wasn't big enough for you to catch. And generally, we think of these consequences not as serious as a type 1 error, right? You're not making any conclusions because you think your treatment didn't work. Where with type 1 error, you're making all these conclusions because you think your treatment worked, but in fact it didn't. Okay, so far we've been talking about what's called two-tailed tests. And so our hypothesis has just been that there will be some change, but we don't specify what the change will be. So because of that, we divide our critical region in two. So it could either be on the very high end or on the very low end of the extremes. Either way, we'll call it significant. So maybe tutoring could make students do better, or maybe tutoring actually lowers their IQ and makes them dumber for whatever reason, it distracts them or something. When we use a two-tailed test, either one we would call significant. But sometimes we have a guess about the direction of change we'll see. And so that's when we start to look at what's called a one-tailed test. And so when a research study predicts the specific expected direction of a treatment, it's possible to incorporate that direction. And again, a directional test includes a specific directional prediction in the hypothesis, and also we consider this in the location of the critical region. Right, so if we have an original population that has a mean of 80 and the treatment is expected to increase scores, then the null hypothesis would state that after treatment, we expect the mean to be less than 80. So basically, there's no increase. And so in this case, what this means is the entire critical region would be located on the right-hand tail of the distribution. Because basically what we're saying is a sample mean that is very large would demonstrate this increase, and that's when we would reject the null hypothesis. So in one-tailed tests, it's hypothesized that the independent variable increases the scores. Then the null hypothesis is that the population mean is less than or equal to that the sample mean is less than or equal to the population mean. The alternative hypothesis is that the population mean is greater than, the alternative hypothesis is that the population mean is greater than that same value, or that our sample mean will be greater than that value. but it will come from a different population. So this shows kind of the region of rejection for a one-tailed test, right? So if we were hypothesizing that our sample mean will be greater, we are just looking at the region of rejection on the right side of the tail. If it's hypothesized that the independent variable will cause a decrease in scores, then the null hypothesis is that the population mean is greater than or equal to a given value, and the alternative hypothesis is that the population mean is less than the same value. So here, if we're thinking that the treatment will decrease the score, maybe it's this therapy decreased depression. Our null hypothesis is that our mean is the same as or greater than the original population. And our alternate hypothesis is that the sample mean is less than that. And I'll just note here another kind of alternative way of notating the alternative hypothesis is HA. We typically use H1, but that's another way of describing it. So here, our region of rejection is on the left side. Okay. So again, this changes. Remember, with a two-tailed z-score, or with a two-tailed test, our critical region at 0.05 was 1.96. When you do a one-tailed test, your critical region or number for z is 1.64. So that changes as well, and we'll discuss that a bit more in class. Okay. Just a couple other notes. So some scientists have expressed concerns about hypothesis testing, particularly when it comes to establishing basically how big of a treatment it had. So all we can say with hypothesis testing is how likely would it be to get the results if the null hypothesis was true. And what it means is we can talk about the data, but not the actual truth of the hypothesis. It also, another problem is that a statistically significant treatment effect doesn't necessarily mean a clinically significant or substantial effect. It's all about the size of the effect relative to the sample error, not the absolute size. So is this a meaningful effect? So these are some criticisms of hypothesis testing. And so some researchers, or often in addition to hypothesis testing now, we use what's called effect size. And so the goal of effect size is to measure the absolute size of the treatment effect that's not influenced by the sample size. So remember that when we're dealing with hypothesis testing, our standard error of the mean is going to be influenced by sample size. When we look at effect size, we're really looking at the magnitude of the treatment effect independent of sample size. Okay, so what we use, the most common use of effect size or way to measure effect size is Cohen's d. And so Cohen's d measures the effect size in terms of the standard deviation. So for a z-score hypothesis, we're looking at the mean difference, and the mean difference is the population mean before treatment and the population mean after treatment. We don't know this, so of course we use the sample that got the treatment as an estimate of this. And so the Cohen's d tells us how big the treatment is relative to the standard deviation. So general interpretations are a small effect size would be kind of less than 0.2. A medium effect size would be around 0.5. So essentially what this means is the difference between the treatment and the no treatment group is about half a standard deviation. And then a large effect size would be a d of bigger than 0.8. So again, this is 0.8 of a standard deviation. A final note is this issue of power. Instead of directly measuring effect size, another way to look at this is detecting power. And power is also about determining the size or strength of the treatment and our ability to detect that. So power is the probability that a test will reject the null hypothesis if the treatment really has an effect. So how likely is it that you correctly reject the null hypothesis, that you correctly detect an effect when it's there? If the treatment has an effect, there are two possible outcomes, right? You correctly detect that effect, and reject the null, or you don't reject the null and make a mistake, which is basically type 1 error. Often, power analyses are required by grants and other kinds of proposals to determine how likely it is that your study will detect an effect that's really there. So power depends on things like sample size, how big we expect the treatment to affect to be, and the value of alpha. This is just kind of a demonstration of what we're studying. So the left side is a distribution of the sample means if the null hypothesis was true. You can see the critical regions are in these tails. The right side is what would be added. This is looking at an 8-point treatment effect. And this is what it would look like if there were in fact an 8-point treatment effect. And what you can see is that virtually every possible sample mean would be in the critical region. If this is your null hypothesis, if you really have an 8-point difference, then almost every mean that you find would be in that region. And you'd say that the probability of rejecting the null hypothesis, the power, is nearly 100% if there's actually an 8-point treatment effect. So this would be a study with a lot of power. Okay, so we'll go over more examples in class, but this is just an introduction to hypothesis testing.